Good day everyone, my name is Gilbert Bigras. I am a pathologist working in Edmonton, Alberta. I would like first to thank the organizer of the Canadian Biomarker Quality Assurance for the opportunity to do this talk. My talk is a practical one to demonstrate how to use an open source software, QuPath, capable to do image analysis on whole slide image. And the example today will be about measuring the KI67 index proliferation on a whole slide image of a breast cancer core biopsy. All this video is recorded and can be found under github.com/Gilbert Bigras. Since a couple of years, software like QuPath and others can address the problem of images generated by scanner of histological slides because the obtained images are gigantic, and thanks to the pyramidal storage we can now navigate seamlessly through whole slide image. And this was the beginning of serious image analysis to be performed on whole slide images. So if you Google QuPath, you will find the website, which is comprehensive with all the required explanation tutorials. And this software can be installed on Windows, on macOS, and Linux. The installation is relatively straightforward. It's worth mentioning that this software is gaining in popularity since it was launched in 2017. The number of publications is growing exponentially, and this is explained by an increasing larger community supporting the software and improving it over time. I just opened my QuPath software by clicking on its icon, and the first thing we'll do is to close this welcome window, and we will start a project. So in order to do a project outside the software, you will create a new folder that you will call the name you want. In my for today I will call it QuPath demo, and this empty folder I will drag it and drop it on the software, and then QuPath is asking me if I want to use this directory for the project. I will say yes. Now I have my project open and I want to add some images. I click on this and the software is inviting me to drag and drop some images. So I already have stored all slide images in a dedicated folder, which is this one. And I will drag and drop, for instance, 2 images. First one and second one. I can now close my file manager, and I will ask QuPath to import these 2 images. Now I have these 2 images. I will open one, the first one at the top, and the system is asking me what type of image this is, and I will say it's an imetoxylin dab, and I will apply. So the first thing you will notice is when you click on image, we have the characteristic of this image, the name, the size, and eventually some characteristic related to imetoxylin and dab. QuPath is like a Perio software. You can move around, you can explore at higher magnification, and you can see the navigator little window here, and I can move around. We will open under View the brightness contrast functionality. This permits to change the color space of the image. Right now this is the RGB color space, but I can switch to another color space like imetoxylin. So now we only see the methoxylin like if it was a negative control. But you'll notice there is some imperfection. The very dark blue is actually some kind of a residual dab, because if I click on this, you can see the dab. The reason for that is the software provided these vector value by default, and these are not precisely reflecting what these vectors should be, because different stain will produce different type of vectors. So I come back to my original picture, and now I will show you how to improve or precise the real value of these vectors. So we need to do a little rectangle annotation, and first of all I will do a rectangle where I can take significant amount of imetoxylin, dab, and also background here. And in order to get the vectors, we go in Analyze, Pre-processing, Estimate Stain Vectors. We click on Yes, and you see the the vector representation, and we will click on Auto, and we'll say OK. And we'll give a name, HDAB estimated, that's fine, OK. And now if I look on my imetoxylin vector visualization, it has improved a little bit, as well as for DAB. This is very important to improve the cellular segmentation as well as the DAB quantitation. This step has to be done for different type of stain that you might use. First of all, we need to do some annotation. I need to annotate the entire core. In order to do that, I can use one of these annotation tools. I will first use the polygonal tool. That's one approach. I can use another tool, and let's first destroy this object that I just created. And I will use now what is called the magical hand, I believe, this tool here. So we will keep this one, and in order to unselect this tool, I can use the move tool. So we're almost good. Before I proceed with the cellular segmentation itself, it's a good idea to experiment the cellular segmentation on a smaller area to make the analysis quicker. That's why I'm creating a second annotation, a square. And if you click here, you'll see that we have the whole annotation for the core and my small rectangle, which will be used for adjusting the parameters for the cellular segmentation. Okay, now we'll proceed with the cellular segmentation, and I will work on this little square only for the beginning. In order to proceed with cellular segmentation, you go on Analyze, Cell Detection, click on this menu, and we will start the cell segmentation right away with the suggested parameter, and I will run it in the little square. You see it's quite fast because I'm limiting my adjustment of parameters on this little square. If I look around, you will see that the parameters, suggested parameter, are missing a couple of DAB nuclei. The reason for that is if we click on the DAB color space, you see that the imetoxylin color space because this is the suggested color space. You see that a couple of dab are literally almost white. That's the reason why we don't see them at all. So the best way to do cellular segmentation is to use what we call the optical density sum, and it's here, optical density sum. And if I click on optical density sum, you will see that all the dab will be clearly visible and they will be properly segmented. So I selected optical density sum. I will switch back to my original image and check carefully here the nuclei, and I will rerun. Way better. We have all the nuclei we wanted to see. I will not discuss the rest of the parameters, which are important, but the most important thing was to mention which color space we have to use to a proper segmentation. So we will now do cellular cell detection with positivity. I will open Analyze Cell Detection, but Positive Cell Detection. It is actually the same type of software, except that we had the capacity to detect a positive nuclei. So I will close this here because it's the same type of parameter. The only thing is we need to change again from a methoxylin color space to optical density kind of color space. And I will close this and I will rerun the whole software and see what happened. Oh, you can see now that pending a certain threshold here, 0.2 optical density, and if I remove the mask with this tool here, you see that we are capturing positive nuclei. However, we're not done because that parameter of threshold can be adjusted. And if you look in this plane here, we have two small nuclei that we can declare that should be called positive. So if I click again on these, you see these two nuclei are called negative. I will take the one which seems to be with the weakest staining. I will double click on it, and you can inspect the specific nucleus here in the hierarchy. This is exactly this nucleus, because if I click on this one, for instance, this is the nucleus. So I come back to this one, and I can inspect what is the nucleus DAB mean, 0.17, and my threshold is at 0.2. I will, because I know that I have other nuclei which are even weaker than that, I will put the value 0.1, and we will rerun this and check what will happen with this nucleus here. They are both positive. Actually, you notice it took a little bit more time. The reason for that is I, by mistake, asked the software to do the segmentation on all annotation, and beyond the rectangle, now we have the entire core, which is the cellular segmentation is done, and the positivity threshold is established. So interestingly, if you click on this tab for annotation, you see my square, which is here, and you see the whole core. When I click on this, you can see the results of our positive detection. So we detected 70,000 nuclei, and the percentage positivity is 24% for the entire core. If I only look on this little square, the positivity is lower, limited to this little square here, but for the entire core, we are at 24%. Now I want to classify the tumoral versus the stromal component. The first step which you have to do is to add features which will help for classification. This is done in calculate features, and we add smoothed features. This is 25 micron around each nucleus that will be looked at. We do that one, and you repeat at 50 micron, and it will create another set of features looking around each nuclei. And we're ready. The next step is to draw some annotation in tumoral area. So I will first do this annotation in this piece of tumor, and I will set the class as tumor. I will do another one, why not, in this spot here. That's a good sample of tumor. Set class tumor, and now I need stromal cells, so I will declare this as stroma, and maybe this spot as well. Class stroma, and this is a good spot as well. So I'll take this one, call it stroma. Okay, if I click on the mask, I will launch the classification so you can see it live. Train object classifier. I change almost nothing here. I keep random trees, which is a good machine learning algorithm. And I will click on live update. And almost instantly, you can see that I obtain quite a good classification on the entire core. I can do more refinement, but it was just the idea to show you how we proceed. And this changed a lot, the result, because if I click on my annotation, the percentage of tumor positive, sorry, this is not the right annotation. So here we go. The tumor positivity increased from 24, now it's 28, because I removed significant number of nuclei, which has nothing to do with tumor KI67 quantitation. In conclusion, this tool, as well as other softwares, including proprietary software capable to manipulate whole slide image with their capacity to detect positivity and classification, are great tools, but limited by a number of factors. And here is a list, like pre-analytical issues. You perfectly know that poorly fixed tissue will not deliver the expected KI67 index information, how powerful the tool is. We also deal with analytical issues. We need to calibrate the IHE assay to deliver the same type of information using, for instance, calibrator. And this is one of the goals of the phase 2 Canadian ring study, to increase the robustness of interlab IHE assays of KI67. We also need to train people because these tools are getting easier to use, but nonetheless a minimum of training is needed. We also need to agree upon standardization of parameters, especially, for instance, how do we establish a threshold to decide what is a negative nucleus versus a weakly positive KI67 nucleus. We also deal with equipment costs. Computer and scanner are relatively expensive. One big final problem is IT interaction. It's not that easy to connect a new type of instrument with the current LIS. This is quite a challenge. Finally, I put at the bottom the web address where this video will be available, as well as other material, including I will put in this site a checklist of all the steps you need to go through to achieve the same result which was presented. I thank you for your attention, and I thanks again the organization of this meeting.